The extreme value theorem is one of only a handful of named theorems that we encounter in Calculus 1. And it's really a consequence of continuity, this theorem is. And so for a theorem, we have hypotheses and conclusions. And so let's go ahead and write out what the hypothesis is. A hypothesis is something that has to be met so that we can come up with a conclusion as a consequence. And so the hypothesis is f of x is continuous on a closed interval AB. And so there's two real key words here in this hypothesis. We've got continuous and we've got closed. And so those are the main things that we've got to really pay attention to. If our function's continuous, if our interval is closed, then we can come up with this conclusion. And so the conclusion here for the extreme value theorem is there exist values capital M and little m. And these capital M and little m are going to be our global extrema. These capital M and little m, or it's going to be the locations of the global extrema, excuse me. So those capital M and little m are in the closed interval AB. So they're the locations that give us our max and our min value. So we'll say such that. When we plug in the capital M to the original function f, it is the maximum value. So maybe I shouldn't say equals here. I'll just say is the maximum value. And when we plug in that little m, it's going to be the minimum value. And by minimum and maximum value, we're talking about minimum and maximum value of the function. So we'll say of f of x on the interval that we're paying attention to. So on the closed interval AB. Okay. And so this extreme value theorem, we need to know where we can find these. Where do we have to look to get the max and the min? So we've already talked in calculus about local extrema, local maxes and mins, peaks and valleys that we might see for the function. And local extrema happen at critical points. And so here for this particular picture, we could see like local extrema here at the top of the two peaks that we see. And we have a local extrema, a local min there at the origin where we have a local min there, a valley. Okay, but those are only local extrema. They're not talking about the global extrema on a particular interval. So you see on my x-axis, I have an A and a B listed here. So that's giving us this closed interval. And so notice that the function values of those endpoints are indicated here. So we've got the f of A slightly positive and f of B slightly negative. And so now those locations in some sense are the places we need to consider when we're thinking about global extrema. So first and foremost, even though this point right here is coming from a critical point and it is a local max, we completely ignore this point here because it's not in the interval. So that's the main thing to think here. It's not in the interval, we're not going to consider it at all, even though it is a critical point. So I'll say critical point, not in the interval. Okay. So now take a look at the four remaining points. All four of those remaining points do come from values that are in the interval. And if you look through here, we've got the smallest one over here at an endpoint. So the min is actually going to be at an endpoint for this particular example. And the highest point that we have is right here. So the max is actually at a critical point. I'll just do CP for critical point. Okay. But then notice here that we have a local min, but not global. At that particular critical point. And likewise here at the endpoint A, we actually end up having a local max there too, when we're restricting our vision only to the interval AB. So we have a local max, but not global max. At the endpoint. And by max here, I guess I should have said global max. And min here, I should have said global min. Okay, so these are going to end up being the important answers that we get from the extreme value theorem.